Hey guys, Dr. J here, and in this video we're going to be talking about separation of variables and how we can use Laplace's equation, or I should say, how we can use harmonic functions to solve Laplace's equation. So Laplace's equation I've got written out here, and I've got its vector form here on the left. So sorry, that's a little hard to see, del squared of phi is equal to 0, which another way of just writing del squared phi is as this. So this is exactly the definition of del squared phi. Del squared phi, that means partial squared phi partial x squared plus partial squared phi partial y squared plus partial p squared partial z squared equals to 0. This is what Laplace's equation means. Same thing, just written out in two different ways. So the classic way of solving these problems is to use something called separation of variables. And the assumption that we make here is that we can write the scalar field phi as a product of functions that are related to one coordinate axis only. So we can write of some function of x, and I apologize, I don't particularly like this notation, but this is the classic notation that's used. So we have a function of x, and we use capital X, but it's just a function, some function of x times some function of y times some function of z. So this is called separation of variables. We're going to assume that our function phi can be written in this way. And then we got to just figure out what x, y, and z are. Now, if we plug this whole thing into Laplace's equation, we get the following. So that's, if we just plug this into that equation, we work out the math. I'm not going to go through all that math, but we work it out, and we're going to get the following. Right, so in this case, we're taking the second derivative of x with respect to x. Each term depends on a different variable. So therefore, because it equals to 0, each one must be a constant. So then we can solve for what those constants are, and you get a solution, which is an exponential. So then the solution, for example, for x, hopefully you can see that. So the function of x, which is going to be plugging back into here, is going to be an exponential, which is plus or minus kx, that's just some constant, times the variable x. So we have an exponential. Right, so what we have, so then phi is simply the product of three different exponentials. It's an exponential that looks like this, an exponential that looks like this with a ky and a y instead of an x, and that would be our y function. And then our z function, because these things have to cancel out and equal 0, our z function has a particular form that it takes. So, and I'll just kind of, I'm out of room a little bit, but let me maybe write it over here. Kz is equal to negative. Okay, so the idea here is that the z term is constrained once we specify the x and the y. What this means is that if you have phi varying a particular way, as there's exponentials in the horizontal plane, then we can specify how phi is behaving in the vertical plane. And altogether, we can now use these things to solve for we can use these things to solve for what phi is given some boundary conditions. So now we have the general form of the equation. Given some boundary conditions, we can decide whether this should be plus or minus or both, and we can solve for what phi should be. So this is in Cartesian coordinates. Laplace's equation in spherical coordinates are a little bit more complicated, but because we're going to be looking at radial fields like gravity and magnetics, they are actually going to be very useful. I'm not going to go through the whole derivation in the spherical dimension, but what I am going to do is we can still write this. We're still going to write phi, and I'll use a different color. We're still going to write phi as a product of three terms, right? We're in three dimensions, three-dimensional space. And so we're going to need three coordinate systems. And so we're going to have some functions which are functions of radius r. So r will be a radial function. And we've got a function of theta. And we've got a function of lambda. And how do you say that? There we go. So these are capital and lowercase Greek letters. Well, this is r, so a function of radius, a function of Greek letter theta, that's an angle, and a function of Greek letter lambda, that's the other angle. So this is spherical coordinates, right? So we have like a longitude and a latitude angles that are associated with spherical coordinates. Now, if we consider just the radial term here, the radial term is going to have a power law form. So power law form here where we have some exponential n and some negative of that exponential plus 1. A and b here are just two constants, so this is like a general form. And again, if we wanted to get specific, this is what you would do in a PDEs class. You would solve for, what these coefficients should be to satisfy our boundary conditions for any particular scenario. If we were outside the Earth, outside of all sources, we would probably want solutions that look like this, where there's this negative power law decay with distance. So the potential is decaying with distance. That's a very common type of solution. And so solutions for lambda are just exponentials like we talked about before. So, and m here is, again, some constant, some complex value constant. So this is a complex exponential. So that's for lambda. Here's for our r theta. There's going to be some general solution, which is going to be, these are the associated Legendre equations. So Legendre polynomials, Pn, Legendre functions, Pn and n and m, and then this is some function, and we give it cosine theta as our input to those functions. So these are Legendre functions. For m equals 0, these reduce to the Legendre polynomials. Okay, all of that to say, our final solution as a function of spherical coordinates now, let me erase all this. Okay, so we're going to have, let me write down the entire solution for phi in spherical coordinates. And so this is going to be phi, the scalar potential phi in spherical coordinates. So r theta phi lambda. And we're going to end up having a sum over Legendre polynomials, but I'm going to skip that part for now. It's going to be 1 over r to the n plus 1. And this is going to be outside exterior solutions. So no sources. We're outside of all sources. And then we're going to have our exponentials. We could write these as exponentials, complex exponentials, or we could write these as sines and cosines. I'm going to leave it in the complex exponential form, e to the I m lambda. Those are our complex exponentials in lambda. And then our theta term is our theta polynomials, our Legendre polynomials.
Oops.
And then what we're going to have to do is we're going to have to sum over m Sn. And it's actually a double summation. But I'm just going to sort of simplify the notation. So the sum over all m and n of 1 over r to the n plus 1. Make sure I get that right. Yeah, n plus 1. Then we have cosine I m lambda. And then we have our Legendre polynomial functions, p of n and m. And cosine theta is our input. So this is exactly the spherical harmonic expansion of the geomagnetic field. That's IGRF, the International Geomagnetic Reference Frame. This is how we write that out. It's a harmonic scalar potential field, and we write it out in terms of these three factors, a factor of radius, factor of lambda, and a factor of theta, those two angles in the spherical coordinate system. So this form is exactly what we're going to have to work with when we get to, yeah, I know, you're really excited. This form is exactly what we're really going to have to work with when we get to looking at full expressions for gravity and magnetic potential fields in spherical coordinates. And in particular, this is exactly the form used, and actually I think the IGRF uses the cosines and polynomial forms, but you can turn an exponential, complex exponential into sines and cosines. That's the form that one uses for the IGRF. The notes also has cylindrical coordinates. I'm not going to go into those right now, but you can check those out. Those solutions turn out to be functions of course, radius and angle, or I should say height and height, radius, and angle. And you get Bessel functions of radius. You get exponential functions of z. Okay, so again, the details on those topics are in the notes, and I will see you in the next video.